Hi, this is my first time at this workshop, so actually I do hope that what I say will not be yesterday's news to many of you. I come from Konrad Banaszek's group, and so even if some of it is already known to you, still this talk is also a kind of an advertisement for this OKD scheme. But let me start with DIQKD. So we all are used to quantum key distribution, this idea, or you can even say this beautiful theory. Let me maybe move this.
Yeah, you can move it.
This theory that when you have two distant parties, basically then by having some quantum devices, they are able to generate cryptographic keys between one another without having to meet physically. And these keys, well, thanks to properties of quantum mechanics, can be made fully random and also fully private, that is unknowable to any other potential malicious adversary. And in the realm of quantum key distribution, I would say that the most extreme version of this is device-independent quantum key distribution. And the notion of device independence, or maybe the goal, is to actually get rid of as much, you could say, perhaps unnecessary assumptions as possible. Because what if, for instance, you buy your devices and it turns out that the person that you bought them from is actually the malicious eavesdropper that you want to, that you want to protect yourself from. So in device independent, we limit the set of assumptions, and we actually treat the devices of Alice and Bob simply as black boxes into which some inputs are given and some outputs are recorded. And the security can only be derived from those outputs themselves, so only from the statistical correlations of what the parties see. So even if they bought the devices from Eve, if you can prove that you can sometimes prove that this correlation is still enough for them to have a secure way to generate those keys. Now, naturally, because you limit this set of assumptions, the trade-off is that you actually require very good experimental fidelity in your setup. And we actually showed a few years ago that a good experimental fidelity is actually an understatement, because even there are some correlations that are barely non-local, so we could say that they are worthy of a Nobel Prize, and still, if the devices share such non-local correlations, which are very quantum, there are protocols of DIQKD in which this is not enough for security. So that's why we think of this paradigm as a kind of perhaps maybe science fiction for now, or at least a thing very hard to realize experimentally. But even having said that, this story about Alice and Bob possessing some devices and generating keys is a sort of fairy tale by itself, because this is not how communication links work. Because while we were all thinking about quantum mechanics, engineers have been building communication infrastructure that works. And throughout those years, this infrastructure has assumed a structure with so-called layers. There are OSI layers, also TCP IP layers. Basically, what this all means is that the way in which messages are sent from A to B is very much, according to existing standardized protocols. Now, very roughly, what these layers mean. So say that Alice wants to send something to Bob. So, for instance, an email. She opens her email application, and this is the application layer into which she inputs the English plain text message. Then the data gets transported by the so-called transport layer, which kind of segments it, puts it into standardized blocks, for instance, controls the order of data that is sent, and controls the flow of data. Then this is given to the so-called network layer, whose goal is to decide on how to send this information through the network of many devices, such as routers or some other modems. Basically, what path to choose that will be the best. There is also the link layer that works between local devices and ensures that they can understand each other. And only after the action of all of these, abstraction layers is completed, and also an important note, this is all done on bit data, only then we have the physical layer, so the thing that we are actually interested in, at which the information gets modulated into physical carriers such as electronic or optical signals. So all of these discussions on QKD basically happen here. And sometimes I get the impression, or at least how it is taught in schools, that this stuff is a bit forgotten. And understandably so, because when I look at it, I already start to get a headache. But see, because this infrastructure is already put in place by engineers, it already has a lot of protection mechanisms and practically a whole zoo of them. And so sometimes this physical layer security is in our circles sold as like the end all be all solution to security, whereas we already have a lot of it. And thus, what I would like to advertise is actually thinking about physical layer security as sort of an addition, a booster. But let's forget about this for a moment and focus on this physical layer. So how is it, you could say, better than all the other methods of security? Well, basically, because it allows all of these methods, they work on data, and their security, you could say, is computational. So it relies on the belief that some problems are hard to solve. Perhaps the most famous one is RSA, where the belief is that factoring large numbers is hard, and that's what many of these protocols base their working principles on. Whereas physical layer security promised to achieve something better, that is information theoretical security. You could also say mathematical security, so truly unbreakable cryptography. And basically, you can identify two ways in which this is done, and this is done thanks to the physical characteristics of the channel that you have. One thing that has been studied somewhat and maybe not that much anymore is a wiretap channel. So there are some channels in which you can certify that even if an eavesdropper is present, then still they have a lower SNR, signal to noise ratio, than the person that you are communicating with, Bob. So if Eve has basically achieves a worse signal than Bob, then there exists specific codes that Alice can use to encode her information that has the effect that this communication is error-free and also secure from me. But more often we think of physical layer security in terms of key distribution. So using the randomness inherent in the communication channel to generate secret keys, and then these secret keys can be used for the purposes of so-called private key cryptography. So all of these computational methods, you could say, you could say these methods are computational security, and private key cryptography is this information theoretical security. But again, although this is the promise, then we have to remember that this is still has to be placed in the context of what the networks look like today. So to be immediately relevant and usable in the very near future, those solutions that we propose for physical layer security should coexist with the standards of today. And also, what I propose is to not think of this stuff as a cure for, I don't know, this is the famous story that RSA will be broken by quantum computers, so here's QKD, but rather it should be thought of as a cyber immunity booster that should work with all these other security mechanisms. So one can ask oneself a question whether this is something that is promised by QKD or not. However, what I would like to now advertise to you is a sort of different method for physical layer security that actually fulfills those two conditions. And this is so-called optical key distribution. So the name quantum is gone from its name. So now this is just not QKD, but OKD. I like this name. And the idea is actually quite simple. So Alice basically will be sending pulses to Bob, and she will modulate the intensity of the pulses. So for 0, she will send a slightly weaker pulse, and for 1, a slightly stronger one. So you can think of it, for instance, in the context of satellite to satellite communication, or maybe I should rather say just free space for now. And so she has her laser and she sends those 2 pulses, and Bob, with his telescope, recovers those pulses. And due to the stochastic nature of photo detection, you could say of this Poisson noise, these pulses will get kind of smeared out. So if Alice sends, for instance, the pulse A equal to 0, the actual intensity detected by Bob, you could also think of it as the number of photons, will have a sort of like Poisson distribution. So sometimes Bob will record, a bit more of the photons, a bit less. The same goes for when Alice sends the pulse number 1. So the idea of OKD is to basically keep only the rounds in which one of the tails of these distributions was detected. So for instance, when Bob detected the intensity on the very right tail of here, then he can be pretty sure that this was the pulse A equal to 1 sent to him, and he can record the outcome B equal to 1. And yes, so maybe here what we have is basically intensity modulation and Nyren detection, which means that to do this just on this line, current technology is perfectly okay to achieve that. But of course, we always care about the eavesdropper. So we also assume some Eve basically hiding there in the background, perhaps with an even larger telescope. And here the sort of like downside of OKD is that it assumes a very weak eavesdropper. So in QKD, and especially in DIQKD, we attribute a lot of power to eavesdropping. And here we will only assume passive eavesdropping. That is, what is only possible for Eve is to detect a part of the signal that is sent to Bob. Maybe not even the part. It can actually be larger. Eve can have a larger telescope and detect more, but still she does not interfere with the channel itself, only listens to it. And like magic of this stochastic nature is that even if pulse A equal to 1 was sent and Bob detected a value at the tails, then the detection of Bob within this red probability distribution is independent of Eve in this red probability distribution. So it is very actually improbable that both Bob and Eve detect a value on the tail of the distribution. Most often it will happen that if Bob detects something here, then Eve, well, she will detect probably, she can detect still something in this probability distribution, for instance, in the middle or even on the red. And when Bob will accept this round as a 1, Eve will have no idea roughly what happens here. And if you analyze it theoretically, as done in those papers, then you can actually prove security in this fashion. And well, first of all, the key rates that can be achieved here turn out to be quite higher than QKD, perhaps not surprisingly, because you very much relax your assumptions on security. And well, you can even say that you are not very quantum anymore. But well, something for something. What I like most about OKD actually is that it can be very naturally connected with a communication layer, because you can actually communicate, so send information and perform optical key distribution at the same time. Because imagine like a sort of, maybe not on-off keying, but a sort of like a BPSK situation, or maybe just rather communicating with a weaker pulse and a larger and a stronger pulse. That is data transmission. So if now Alice actually sends not 2 strengths of pulses, but 4, 2 of them differing very slightly and 2 of these differing very slightly, then at the same time, she kind of imposes the OKD on the communication. So still, whichever one of those is sent, Bob reads as a communication of bit 0. Whichever one of those is sent, Bob reads as communication bit of 1. But if Bob then again does this thresholding for the tails of probability distributions, sometimes he can also generate bits of the secret key. So it turns out that you can do both simultaneously. Simulations for instance, for a satellite overpass from a LEO to ground link have been made here, suggesting that while gigabits of information can be sent at the same time, even if Eve has a 3 times or 10 times as large telescope as Bob, they can still generate megabits of key for such a single pass. And as I said, this is very easily implementable in an existing layer model. And also it aids the model, because many of these methods that I've shown briefly that work at these other layers, they also sometimes need some bit of like perfect, fresh randomness. I mean, they reuse their keys, but if you, for instance, can replace those short random keys, these methods work better. So in OKD plus communication, what you can do is that not only you can use those keys generated here to strengthen the privacy of this communication, but you can also use these keys and supply them to all the other previous layers to increase the security at these layers. So it has like an advantage in more than one place of this whole picture. So what I tried to advertise to you is that actually this physical layer security is not just quantum key distribution, it is actually a spectrum of many methods. And not only is it a spectrum with very many options that you could perhaps order that some are more secure, but maybe less applicable now or less realizable at this moment. And at the other end, you have something that is less secure, you could say, but more available. But still also, I think that we should think of it as just another dimension of information protection. So if there is this trade-off between protection level and cost reliability, and I'm not proposing to I wouldn't dare to forget about QKD, but only to realize that it will take time and technology. So perhaps in the meantime, it would be a good idea to think of some, you could say, low-hanging solutions like OKD that could be implemented in the communication infrastructure even today. Thanks.
Any questions? Yeah, thanks for your presentation. Is this just for free space, or is it for fiber, and how does it prevent E from just having the same key results? I did not understand that step, sorry.
We think of it primarily in free space, but it could also be realized in fiber. But in free space, you have this nice picture of, one receiver telescope, and perhaps because of diffraction, the signal that you send to it is sort of, lost also, or maybe leaks out of it, and you can imagine a potential third party collecting a part of the signal. And again, why does this allow for a secure key generation? Is because if a pulse like a equal to 1 is sent, this curve represents the probability of detecting some intensity of the pulse by Bob, and this by Eve. And the thing is that within those probability distributions, what Bob detects here is statistically independent from what Eve detects here. The only thing that is common, the correlation, is that they both detect the red probability distribution because Alice sent a equal to 1. But within this probability distribution, it is random what Bob records, and it is also random what Eve records. And Bob, controls the protocol between Alice and Bob, and he tells Alice to only keep the rounds in which he recorded a tail of the distribution. But it is more probable that actually in those rounds where Bob recorded the tail of the distribution, well, Eve will sometimes also record this tail, but sometimes she will record this tail, and sometimes she will record a value in the middle. So we base here the security on the fact that Bob dictates which rounds are safe and which are discarded. And within the rounds that Bob saves, Eve actually has less knowledge. I mean, she has no knowledge no good knowledge of what bits have been kept. I know that makes more sense now.
Nice talk. I mentioned many security talks, and this is the first one that said there's a lot of security at all these upper layers. So kudos for that. I have a bunch of questions about this slide here. First, are you making what assumptions are you making on the transmitted states? Are they coherent states or okay, so it is coherent states, right?
Yes, I mean, I believe in this works it was assumed that they are basically coherent states.
All right. So in that case, there's if you model the channel as a beam splitter with perhaps. Do you have any noise in that beam splitter? Is it a lossy thermal noise channel, or is it just pure loss channel?
I believe this analysis was work for a pure channel.
Okay.
I'm not certain.
So, but here in the states, you should not have any classical correlations between the two outputs. But if you have thermal state input or thermalized input, which you're going to have on a real system, there are going to be classical correlations. So what would happen if there are in fact classical correlations between Bob's and Eve's output? Will there be sufficient to increase that gap, or will you have to rethink your system entirely by using some kind of distillation procedure?
Yes, for sure. Very good question. For sure, working with there's a lot to optimize here. That the strength of these pulses, also this thresholding where it happens, and where such correlations occur, such classical ones, probably it will lead to the that one would have to move these thresholds even further, which will reduce the queuing because it will reduce the percentage of rounds that are kept. We started looking at it a bit. Actually, we gave this to one student, but he stopped responding, so we'll have to be revisit it ourselves. I'm not sure whether, I don't think it will break it because this is all still very kind of carefree, but probably just diminish the queuing.
And do you assume implicitly the channel from Alice to Bob is better than the channel from Alice to Eve here?
No, actually we do not. Or actually we do the opposite, more rather. Usually we assume, for instance, that Eve collects 3 times as much of the signal as Bob, or even 10 times as much. With this also, this has an effect on those probability distributions. They are basically much wider. But I mean, they are not wider one thing, but also those peaks are further apart from each other because the stronger signal is kind of like at the same time easier to differentiate between those two pulses, but also they have more variance. So of course, this does diminish the ability to generate the key, but surprisingly slowly.
Right, thank you.
What about amplifiers on the line?
Amplifiers.
Optical amplifiers, yeah.
That's what I was talking about when things thermalize,
It doesn't work anymore, right? So this procedure will also be limited then to 30 kilometers in commercial fiber, yeah?
Good point.
But he said that they tuned correlations, so they can feel.
The other question is how wide, what are we talking about here in the statistical widening of that on the right side? What is on the x-axis?
On the x-axis,
In numbers.
well, you could think of it like at the x-axis, let's think of it as the number of photons detected.
Yeah.
So when a coherent state to some strength
The
comes,
y-axis is the number of photons detected.
no,
and the x-axis?
the x-axis is the number of photons, the y-axis is the probability of detection. So it's a Poisson distribution of a coherent state.
Okay.
And you know, Bob has a coherent state of strength something, Eve has a one of, well, you could say for instance the same strength, but the number of photons actually detected by Bob has not to be the same as by Eve, because basically these distributions are not peaks, but they are like spread.
Thanks again.